Hello, good morning, good afternoon, and good evening to everyone. And thank you for attending this Aber Instruments webinar, which will cover yeast management in the brewing industry using the Aber Yeast Monitor. My name is Rhys Jones. I'm the Product Applications Manager for Aber Instruments, and it's a pleasure to present to you all today. I hope you find this webinar informative. So let's begin. During the course of this presentation, we'll try to cover a few of the basic topics: who we are, the basic principles of the Aber technology, its application, the calibration process, and then the system aftercare. So a brief introduction into Aber Instruments. We are based in Midwest Wales, in the university town of Aberystwyth, which is where the Aber from Aber Instruments gets its name. We are an employee-owned company with over 30 years of experience in the industry. Aber Instruments are the inventors of the technology, which utilizes dielectric spectroscopy to measure live cell concentrations. With the technology being invented and patented by Aber Instruments in 1988, but it wasn't until 1991 that we introduced our first generation of brewing instruments, the 316 model. We are now on our third generation of brewing instruments, and we've become a standard for most of the large brewing groups, with thousands of systems across the world, and some companies using at least 50 systems across their sites. So, how does the technology work? In other words, what are the principles behind the Aber measurement? Aber technology measures two basic parameters. We measure capacitance and conductivity. And put simply, capacitance is the ability of a substance to hold charge around itself, while conversely, conductivity is the ability of a substance to give charge or to allow charge to flow through it. Now, why are these parameters important to us? This is all to do with the structure of the cell membrane. Cells with intact cell membranes, in other words, live cells, do not allow the free flow of ions across the cell membrane. Therefore, under the influence of an infinitesimal electrical field, which is generated by the Aber probes, there's a buildup of charge around live cell membranes. Therefore, every live cell acts as a tiny capacitor, and the greater the number of live cells, the greater the capacitance signal, and it is this signal that the Aber probe measures. When we induce an electrical field via the probe, the negatively charged ions will orientate themselves towards the positive terminal, and the positively charged ions towards the negative terminal, as seen here. The membrane of the live cells prevents the free flow of ions, and so we get this charge separation across the cell membrane, and the cells become polarized. The cytoplasm of the cell and the surrounding media are conductive, while the cell membrane is an insulator. And when we have two conductors separated by an insulator, this is a capacitor. Therefore, with every cell, or every live cell, acting like a tiny capacitor, we can detect the capacitance signal, which is proportional to the live cell concentration. On the other hand, dead cells, which have ruptured or permeable cell membranes, are unable to prevent the free flow of ions as live cells do, and therefore cannot hold charge around themselves, thereby not contributing a capacitance signal to the overall suspension. Therefore, the Aber technology is insensitive to the presence of dead cells. Likewise, other substances found in the suspension, such as trub, gas bubbles, and other solid media particles, do not have the ability to hold charge, and again do not contribute to the capacitance signal, making Aber technology unique in that it is not only detecting the live cell concentration, but ignoring the dead cell concentration. So, what's being measured? As previously mentioned, the Aber probe is measuring capacitance and conductivity, with capacitance being the ability of a substance to hold charge, in this case around live cell membranes, and this capacitance signal is linear to the amount of live cells present. Capacitance is measured in units called farads, but as the signal is incredibly small, it is measured in picofarads per centimeter. Now, obviously, this unit of measurement is somewhat meaningless to a brewery, therefore it can be converted to two recognized lab units, either percentage viable spun solids or cells per milliliter. And this conversion process is performed during the calibration procedure, which will be discussed later, as well as in training videos and other training material, all of which can be found on the ABBA Instruments customer portal. For more information about this, please contact the support team at ABBA Instruments, the details of which will be shown at the end of this presentation. Now, the conductivity, which is of course the ability of current to flow through a substance, is measured in Siemens, or millisiemens per centimeter in this case. While not being the primary unit of interest, it can provide valuable information about the process taking place, whether that be yeast, CIP, or rinsing taking place in the pipeline. Here is an overview of the typical values one can expect to see when the process seen on the left-hand side is taking place, with of course the one of interest being the yeast slurry, which has a typical conductivity range of 0.75 to 1.5 millisiemens per centimeter, and a concentration range of approximately 10 to 65% spun solids. So let's break down what the ABBA system is actually measuring. So just as an example, here we have a centrifuge tube, and if we were to imagine this being filled with a yeast slurry, we would spin that down, which would separate the liquid supernatant and our total spun solids. After separating these and discarding the liquid supernatant, we are left with our total spun solids, but this is not what the ABBA system is measuring. As previously mentioned, the ABBA system is insensitive to the presence of dead cells, as well as trub, gas bubbles, and other solid media particles. Therefore, we can separate these further, and we measure only the live yeast concentration, or the viable spun solids. In other words, only the live, viable portion of the sample is being measured. So, what are the benefits you can expect to see after installing an ABBA system? Unlike traditional cell counting, the measurements are performed in real time, in situ, enabling the entire process to be automated. With the process being automated, the correct yeast concentration can be predicted repeatably, eliminating errors due to dilution during the lab analysis. With repeatable and accurate yeast pitching comes good yeast management and a more consistent and predictable product quality, with a reduction in the risk of hung fermentations or the production of off flavors caused by over-pitching. All of this enables more efficient use of fermentation vessels, with a reduction in deviations in brew length, enabling better planning. And with a known quantity of viable yeast cells, the yeast storage vessels can be more efficiently used. Now we're going to take a look at some data. Firstly, those gathered by BAS brewers, which shows the standard deviation in fermentation times both before and after the ABBA system was introduced. The variability in fermentation times is quite self-evident for the first 10 months, after which the ABBA system was introduced and the variability of the standard deviation was greatly reduced, and the consistency in fermentation times improved. Similarly, at Suntory in Japan, a significant improvement in the consistency of the fermentation rate relative to the target fermentation rate was seen following the introduction of the ABBA monitor. This was compared to their previous pitching method based on offline cell counts. We see an improved consistency in the fermentation rate with the condensing data points post-installation of the ABBA monitor. Meantime in London compared the ABBA monitor to their previous pitching strategy. The graphs here show the fermentation profile based on attenuation for the London lager strain over 4 different brews. where the degree plateau is displayed over time. Firstly, when pitched by mass on the left-hand side, and secondly by the ABBA system on the right-hand side. A significant improvement was seen in the performance and consistency of the fermentations following the use of the ABBA system. The reduction in fermentation time found could result in energy, cost, and efficiency savings. This was also the experience of Summit Brewing Company, who saw a reduction in degree plateau variability over time across multiple brands and brews. This was achieved by improving the consistency of the pitching rate when using the ABBA monitor to control their pitching regimen. The data point distribution was significantly condensed post-installation of the ABBA system across and demonstrated in this long-term study in over 75 individual brews. The reduction in variability could improve the final quality of the product. Therefore, the consistency of the degree plateau trend over time that the ABBA monitor provides delivers predictable, consistent, and greater product quality. Summit reported improvements post-ABBA installation relative to the previous manual pitching method across all metrics measured. The benefits of consistent and repeatable fermentations are well known. They include, but are not limited to, product throughput, effective planning, product quality, and consistency. In this next example, we compare the variation between 5 independent operators performing replicate counts on the same 5 samples. First using the hemocytometer, and then with the same 5 operators performing replicate counts using capacitance technology. The automation of the counting process removes the inter-operator variability across the entire range of dilutions and counts the yeast the same each time, thereby making the process and product more consistent. So, what applications can the ABBA monitor be used for? Now here we see an overview of the entire brewing process, but the part that concerns ABBA in particular is the fermentation, which we'll look at in more detail. The ABBA systems can be used typically for 4 applications, namely propagation, pitching, fermentation, and cropping, though by far the most common applications are pitching and cropping. So let's take a look at these in more detail, starting with pitching. So now let's take a look at how the ABBA can be utilized for pitching. Here we have our yeast storage vessel on the left, fermentation vessel on the right, and these are connected via pipework. Then we have the PLC, which controls the dosing pump, and then we have the ABBA yeast monitor, which provides real-time live cells per mil readings or percent spun solids readings to the PLC. And finally, we have the flow meter, which provides liters per second measurements to the PLC. To begin with, the PLC will switch on the dosing pump and yeast will begin to pass from the storage vessel towards the fermentation vessel. On its way, it will pass the ABBA monitor, which will measure the live cells flowing past it, and the monitor will relay this information to the PLC. At the same time, the flow meter will relay the live volumetric flow rate to the PLC. Now, if the PLC knows how many live cells per mil are passing in the pipeline at any given point, as well as how many liters of yeast are flowing into the fermentation vessel, it can calculate precisely how many live cells are passing into the fermentation vessel and totalize the values. As the yeast continues to flow from the storage vessel into the fermentation vessel, and the total live cell concentration continues to totalize and accumulate, it can do so until it reaches a target cell concentration preset in the PLC for each particular recipe. Once this target is reached, the PLC can switch off the dosing pump and the pitch is complete. The pitching automation allows for accurate and consistent pitching every time. With this more accurate and consistent pitching, to achieve repeatable pitching rates, we can expect a more consistent pitch with shorter and predictable fermentation times. Consistency of product leads to a reduction in off flavors, such as those caused by increased diacetyl levels outside of specification, and an improvement in the consistency of the product quality. Here we will demonstrate what the user can expect to see during a pitch from within the PLC. On the y-axis, we have our totalized live cells, and on the x-axis, we have time. The broken red and blue lines represent the target total live cell count for two different recipes preset within the PLC. Once the pitch commences, the yeast will pass the Aber monitor, at which point the live cells per mil will increase. At the same time, the flow meter signal will also increase and enable totalization within the PLC to commence. The readings will continue to totalize as long as the live yeast cells are flowing in the pipeline. Then, when the totalized live cells pitched reaches the preset target concentration for their respective recipes, the PLC will switch off the dosing pump, and then the pitch is complete. The next application that we're going to look at is cropping. This is much like pitching, except there is no need for the flow meter during the crop. First, a cell concentration threshold must be set in the PLC, for example, 1 billion cells per milliliter. Any cell concentration above this value can be recovered, while anything below will not. Once the fermentation is complete, yeast cells will generally settle into 3 discrete strata in the fermentation vessel cone. At the bottom, you will have your dead cells. Then you will have the majority of your healthy, viable yeast, and then finally the top layer is your juvenile yeast beer mixture. When the cropping begins, first of all, the dead cells will pass the Aber yeast monitor. But because the Aber monitor is insensitive to the presence of dead cells, the live cells per mil reading will be below the preset PLC threshold. Therefore, this dead yeast will be diverted off to waste. Then, as the viability of the yeast begins to increase, the signal from the Aber monitor will increase. As soon as it passes the thresholds, the PLC can divert the yeast back to the yeast storage vessel. Then finally, as the yeast passing in the pipeline begins to become diluted with the beer, the dilution effect will cause the signal to drop, and therefore the PLC, once it passes below the threshold, can divert the beer yeast mixture off to filtration. Here we can see a representation of what one might expect to see on the PLC during a typical crop. As previously mentioned, once the cropping begins, the concentration of live cells will be relatively low, and thus the PLC can divert this yeast off to waste. Then, as the signal begins to increase when more and more live cells pass the Aber monitor, the PLC can divert the yeast off to the yeast storage vessel. And then finally, the signal will begin to decrease again when the beer yeast mixture passes the Aber monitor, and the PLC can divert this off to filtration once it passes below the preset threshold point. Therefore, the Aber monitor not only enables the automated control of your cropping process, but also improves yeast management, as only high concentrations of viable yeast will be recovered and used for subsequent pitching. This threshold can be set in the PLC to any cell concentration value the user wishes to recover. Now finally, moving on to fermentation and propagation applications. These are somewhat less common than the pitching and cropping that we've just covered. However, both applications have been applied with success. In fermentation applications, the Aber monitor can be used both as a secondary reference to confirm the success or accuracy of the initial pitching via the Aber monitor, and as an indicator to stop fermentation at the appropriate time, thereby improving and ensuring product quality. And then propagation applications. The ABBA yeast monitor can be used to monitor the progress of yeast growth and identify the optimal pitching time while measuring the precise quantity of live yeast. So now that we've gone through the principles of the technology, as well as the various applications that it can be used for, let's take a look at how we initially calibrate the ABBA monitor. The calibration and training is typically carried out at the time of commissioning by an ABBA Instruments representative. Then subsequent calibration checks can be made by the brewery staff at scheduled intervals. Each yeast strain requires an independent calibration, which only needs to be carried out once per strain, though each strain's calibration can be refined and improved post-calibration by the brewery staff. The calibration of the ABBA yeast monitor consists of 4 parts, if working with cells per mil, or 3 parts if working with percent spun solids. But as many of you listening may have already calibrated the ABBA systems, in the interest of time, I will not go through the complete calibration procedure, but I will give a condensed overview. Note that the full calibration procedure can be found in video form on the ABBA Instruments customer portal, which may be more helpful than a brief verbal guide now. However, we will go through the correlation check procedure in some more detail, which is important to perform after the initial calibration and then checked at regular intervals. So as I mentioned, the calibration is broken down into 4 discrete parts: the zeroing, the RCM calculation, the percent spun solids factor, and finally the CPM factor. The purpose of zeroing is to remove the background capacitance of water that is present in yeast slurries. Water has an inherent capacitance value as a result of it being a dipole molecule, but as this capacitance signal is not caused by the presence of cells, we want to remove this background capacitance before we begin. Once we have done so, any remaining capacitance would be due to the live cell concentration signal only. This process is much like tearing a weighing scale. Then we move on to the RCM calculation. Each yeast strain has its own unique RCM value, which can be thought of as a strain fingerprint. During the RCM calculation, we identify the RCM value at which changes in external conductivity do not impact the cell concentration. This calibration is fixed and only needs to be performed once per strain. This is an example of the Excel sheet and what you would typically see during the RCM calibration. You can see the intersection point on the graph, which is automatically calculated. This is the point, or the RCM value, at which changes in the conductivity do not impact the cell concentration. While the ABBA monitor measures capacitance, this unit of measurement is not used by most breweries. Therefore, the next 2 steps in the calibration process, the percent spun solids factor and the CPM factor, involve converting this value to match the brewery's chosen unit of measurement based on an offline sample count. And this is broadly the calibration procedure, but as I mentioned before, a comprehensive guide can be found on our customer portal. So, what do you need to do after the calibration of the yeast monitor? Inevitably, during the calibration, where a single yeast cell count is used to set up the ABBA monitor, there will be some error. Therefore, the purpose of the correlation checks is to reduce this error and to bring the ABBA readings as closely in line with the lab readings as possible by performing correlation checks. The ABBA monitor will read as instructed based on offline counts and do so consistently. Therefore, ensuring the accuracy of the offline counts is imperative to effectively set up the system. The correlation checks ensure that an accurate CPM factor is acquired by performing multiple counts and comparisons, building up a robust and reliable dataset, and then taking an average CPM factor. Let's go through this in a little more detail. To perform the correlation checks, all you will need is 3 to 5 lab beakers. an Excel spreadsheet, a pen and paper. The correlation checks may be performed by taking multiple samples from one pitch or a single sample from multiple pitches. Label your beakers according to the sample taken, 1, 2, 3, and so on. As yeast is being pitched, draw a sample from the sample point nearest to your ABBA compact probe. At the same time as the sample is taken, note down the CPM reading on the ABBA screen. Repeat these steps every few minutes until you have drawn 3 to 5 samples. These samples should be taken to the lab where a live cell per mil count can be taken. Input the lab and ABBA values into the ABBA Excel spreadsheet as shown. Along with a current CPM factor, the ABBA spreadsheet will then automatically calculate a new CPM factor for you based on the current CPM factor and the difference between the ABBA and lab readings. After all the samples have been input into the spreadsheet, an average of the new CPM factor should be taken and input into the monitor. This will then bring the ABBA readings in line with the lab. This process may be repeated until the percentage difference has been reduced to a satisfactory level. Note that what we're looking for is a consistent deviation or percentage error between the ABBA and the lab readings. This will ensure that when the factor is adjusted, it is adjusted to the correct value. If the percentage error is highly variable from one count to the next, then repeat the process until a trend is seen. In this example here, the CPM factor will not need to be adjusted, as the percentage error is both positive and negative, meaning that the ABBA and the lab readings are in the correct range and hovering around one another. These correlation checks will need to be performed on each yeast strain independently. Once set up, they will remain stable for a very long time. While getting a strong correlation between the ABBA and the lab readings by performing the correlation checks is vital, it is important that we don't lose sight of the big picture. Above all else, we want to achieve greater pitching rate consistency, fermentation time reduction and consistency, improvements in product quality, and vessel efficiency. Occasionally we can get bogged down in adjusting the CPM factor to the nth degree to reduce the percentage error. But there will always be a minor difference between these two measurements, as the ABBA monitor is measuring a different property of the cells than the offline counts, capacitance versus dye exclusion. And the lab readings are also intrinsically prone to compounded errors through serial dilutions, individual interpretation, and so on. Therefore, one should focus first on reducing the errors to a satisfactory level before then moving on to monitoring the big picture parameters. The ABBA monitor should improve the pitching rate accuracy and consistency, as well as the consistency of the fermentation times. These would be reflected in the degree Plato against time, as well as in other metrics, as seen in the summit and meantime case studies. The fermentation time efficiency should be improved as much as it was in the Bass and Suntory cases. These should in turn improve the vessel efficiency, planning, and product quality. In terms of maintaining the ABBA system, it is a very low maintenance and very straightforward piece of equipment. The probe should be checked at regular intervals to ensure that it is clear from debris, though the CIP regimen should take care of this. Then the cables and seals should also be checked annually. Once the CPM factor has been set up, it will remain stable for a very long time, though it can be checked annually along with the zero value. For any further information, general queries, or for any details on how to access the ABBA Instruments customer portal, please email the support team at the following address. Thank you very much for listening to this ABBA Instruments presentation. I hope you found it informative. And I'd like to now open it up to any questions that anyone might have.